Okay, I'm going to start with complete dominance. Monohybrid cross. Okay? So it's complete dominance. So my example, tall is completely dominant, I'm abbreviating dominant, over short. So we have a gene for height and peep length. We have two alleles. Big T for tall, little t for short. So if we cross a homozygous dominant with a homozygous recessive, again abbreviating these, what does that translate to? Homozygous dominant, big T, times little t, little t. We make our Punnett square. This individual, half of the gametes get this big T, half get this big T. This individual, half get this little t, half get the other little t. When we put them together for potential fertilizations, big T, little t, big T, little t, big T, little t, big T, little t. Now we end up with, and I'm going to abbreviate this, so listen very carefully, a genotypic ratio. Genotypic ratio of 0 big T to 4 big T little t to 0 little t little t. See, all of them. So if Mendel did this cross and he had 200 offspring, all of them would be tall. Okay? So 100%. In fact, the phenotypic ratio, P for phenotypic, 4 tall to 0 short. Now, let's take two of these offspring, two of these F1s, and cross them. They're different because we're doing big T, little t, big T, little t. So half of the gametes from this individual get the big T, half get the little t. From this individual, half get big T, half get little t. So we have big T, big T, big T, little t, big T, little t, little t, little t. Now, our genotypic ratio is 1 big T, 2 big T, little t, and 1 little t, little t. Our phenotypic ratio is 3 tall to 1 short. Now, remember, the only one whose genotype is showing is the little t, little t. So these you can't tell if they're big T, or big T, little t. You would have to cross them with a homozygous recessive and determine that. And in fact, you would get, if they were big T, you'd get this. But look what would happen here. If we're looking at these genotypes, when we test cross them with a homozygous recessive, we get a genotypic ratio. Let's make sure that you keep these together. A genotypic ratio of 0 big T, 2 big T, little t, and 2 little t, and a phenotypic ratio of 2 tall to 2 short. All right. Now this is complete dominance. Let's look at incomplete dominance. There's something. Incomplete dominance. Now let's say that curly hair is incompletely, so in a question I would tell you dominant over straight hair. Okay? So we've got the gene for hair texture, right? And we have big C is for curly, and little c is for straight. So big C is curly, little c is straight, but we have a unique phenotype for our heterozygote so that big C has wavy hair. All right? So, if you want to kind of get your thoughts together before you try to do the Punnett square, what we end up with, if we can cross curly with straight. And we get a genotypic ratio 0 big C to 4 big C to 0 little c, and we get a phenotypic ratio. Remember, GR genotypic ratio, PR phenotypic ratio. We get for curly, and you could go on and put these in 0 wavy, because I've said that we've got this, and 0 straight. Now, we wouldn't want to take siblings and breed them like the Mendel could with the pea plants, but if we take two individuals who have wavy hair, so that translates to big C, big little c times big C, little c. And like we had over here, we have a genotypic ratio. When we took two heterozygotes and crossed them, we've got 1 big C, 2 big C to 1 little c, but now all the phenotypes are genotypes are showing with the phenotypes. So, So our phenotypic ratio is 1 curly to 2 wavy to 1 straight. So, complete dominance, incomplete dominance. Next, I am going to do codominance. And why don't we just do we'll do two of them. We'll do blood types and, darn it. And the hemoglobins. Codominance. Now, again, the blood types are a little more complicated, so let's do this. Blood types. A is completely dominant over O. B is completely dominant over O. But A and B are codominant. So if we take someone who is type A but heterozygous, so that means they're AO, and someone who is type B and they are also heterozygous, so they're BO. Notice I'm not picking just the B and doing big B, little b, because they're codominant. So look what we have. AB, B, A, and O. Look at that. Isn't that interesting? So now let's do percents. The probability is 25% type AB, 25% type A, 25% type B, and 25% type O. The two that you can know the genotypes are the AB and the O. The A's and the B's, your A's could be AO or AA. Your B's could be BO or BB. Remember, two alleles. Okay? So this couple, one a type A, one a type B, and heterozygous, could end up having an equal chance of a kid of any of the ABO blood types. But what if we took A, O, and BB? AB, B. AB, B. So that one is different. Notice, it is different. So you can do all kinds of crosses. You can take any of these. Now, if you take two people that are O, their kids are going to be O, because the only type of allele that is present is O. So no A antigen, no B antigen. Hemoglobin S. And hemoglobin A are codominant. Now this one doesn't have a third phenotype in like the type O. So a person can be AA, AS, or SS. So if we take someone who just has hemoglobin A, and they're going to have a kid with someone who is heterozygous and has both A and S, there's a 50% chance that the child will just have hemoglobin A, and a 50% chance that they will, AS is a carrier, but they also have sickle cell trait. Okay? Now, if we take two people who have the trait, so they are not sick with sickle cell anemia, there's a 25% chance that they are just hemoglobin A, a 50% chance that they have both, and a 25% chance that they just have hemoglobin S. This is sickle cell anemia. This is not good. But remember, I mentioned this is an example of pleiotropy. So what happens in areas where malaria is a huge problem? And until about 10, 15 years ago, malaria was a huge issue. It killed, get this, 1 million, about 1 million people a year. And most of them were children under 5 because they have a harder time dealing with malaria. So big. It has come down to